Okay, so we were at chapter 10, which is somewhere on page 2, 5. Okay, so just to give you guys a quick overview of what we've been talking about. So this, especially for Aryan and Deep, the textbook is basically about regression, statistics, analysis, data analysis. So far, we started with like this basic idea of what linear regression is, mathematical analysis of linear regression. Then we moved on to, okay, what about some nonlinear methods? We moved on to these ideas of kernels, what kernel regression is. We took a slight detour and figured out what bootstrapping is. These are all, I'm just saying this so that you're familiar with the terms. You don't have to know what it means. That's what the review is for. Um, and so after a point, like what we're now diving into is what are these assumptions we make when we say we're doing linear regression. Particularly in this chapter, we're going to talk about homoskedasticity and heteroskedasticity. So the idea is when we're doing linear regression, we typically assume homoskedastic data, which is, what does that mean? So I assume that the noise variance is constant for each data point. So my measurements, in a sense, you can say you're talking about your measurements having the same kind of noise drawn from the same distribution. And that distribution has a constant variance. So that's more or less the idea. The chapter focuses on what if that is not the case. What if your noise is drawn from a distribution and is heteroskedastic in nature? And that gets us to this point where we've been talking about giving equal importance to all observations, um, as is generally appropriate when looking at the conditional expect. I don't know how familiar you are with expectations and variances, but if not, then we'll get to that also in the review. Um, so typically you, again, so I'm struggling to like give you all the background of 10 chapters immediately, but bear with me here. Um, yeah, I'll just continue with this chapter as is. So the oldest reason that we want to use weighted least square is to deal with non-constant variance or heteroskedasticity. So there we want to say, okay, if you have noise with a varying variance, so your noise varies with your x, then you can't say all observations have equal weight, because some observations will have a lot of noise, and by definition you won't be able to predict very well there, just because your noise is just very high. And other observations where you have lower noise, you want to learn more from those observations as opposed to the ones with higher noise. That is the general idea behind why we want to weight our data, why we want to use weighted least squares versus ordinary least squares. um, the equation that we used to look at was something like this: the mean squared error. For the parameter estimate, we had 1 by n yi minus xi times beta the whole square. So this was the definition of our mean squared error given this estimate beta, or for our data. And the solution we got was this estimated OLS estimate of the parameter beta. So just again, sort of from the ground up, your y is what the variable, the target variable. Your x is the predictor variable, and your beta are the parameters you fit to the data to be able to make x predict y, in a sense. So yeah, I don't want to say more about this. Yeah, you'll have a detailed discussion in the review. So what they're saying is, now in this case, you're assuming every yi contributes an equal value to the mean squared error. But now if you want to instead weight this, then you add a weight wi for each data point I. So you have n data points because I goes from 1 to n, and for each data point you associate a particular weight with it. um, don't get scared by the math if this is the first time you're looking at it. We all got scared by it initially and we grow used to it over time. That is the way. So that is how you define the weighted mean squared error. Fairly straightforward. Just add a weight for each data point. But this begs the question, like, why do we add a weight for each point? Like, why do we want to minimize this equation as opposed to this straightforward equation where you weight all of your data points equally? Well, he hops on the same point that we started with, that there is higher noise variance at some point, lower noise variance at other points, and so we want to predict where we can actually make sensible predictions as opposed to somewhere where there's a lot of noise and we're not going to be able to make sensible predictions. So focusing accuracy, and this might also be because we care strongly about some response. We care strongly about some values of the input as opposed to other values. So particularly values we see again and again. Here we want to make good predictions, um, and others where he gives an example saying ones where mistakes are especially costly, embarrassing, or painful. Um, Again, interrupt me if anything is unclear, if I'm missing some very fundamental ideas of what X, Y, W are. So typically your, I can I draw here? Um, oh yeah, I can move this out. Use my pencil. So typically, um, just to give you this background, this will be our Y, this will be our X. You have some data. You have some data. Um, these are points. Sorry, you have some data. You fitted a function using this data. Sorry. And now you're saying, okay, if I have a new point where I want to make a prediction of my y for this point x, then I use this function and I say that, okay, according to this linear function, this is the y I'm going to predict for my x. I hope this is clear. If this is not, then please ask me. I will repeat. Oh, nice. And what he's saying is some places will have a lot of noise variance. So if I have some points where like very um, very high noise variance and I have a linear function, I do not want to give these points a very high weight. And making some assumptions here, but just to give you an idea of what it looks like. Like I want to estimate where I have a lot of data and I have low noise variance. Now I won't know this beforehand. So the rest of the chapter is about how, why, and like what function is this? What function does the noise variance follow? And so on and so forth. But we'll get into that later. Right now we're talking about like why exactly would we want to consider weighted mean squared error as opposed to regular mean squared error. So one is accuracy. We care about some values of the input. We don't care about other values. So for example, if I want to make predictions here, these are the points I care about. These are not points I care about. So that is the idea behind the first point. The other idea is the version of the same, discounting imprecision. So there is some theory for this simple statement that we will get into again in the review. But these are like the key. If you want to Google stuff, these are like the keywords you should Google to understand what's going on, or you should read the initial chapters. So ordinary least squares is the maximum likelihood estimate when the epsilon is IID Gaussian white noise. So again, IID is independent identically distributed. So again, we've covered this before, so I won't go into details, but the idea is it's variance is constant. I guess I'll just say that for now. That should be enough. Um, I should probably explain what variance means, um, or I should explain what I don't know how familiar you are with like basic statistics like mean, variance, expected value. But the variance in a very hand wavy fashion, if you have some data that is drawn from a particular distribution, the center or the average or the expected value is this mean um, of the distribution. Again, this is a very hand wavy explanation for the in the interest of time. The variance is like how much does this distribution vary from the mean. So you take each point and you consider its distance from the mean and you square that. So that's in some sense gives you a measure of like how far this is from the mean. So you can imagine some distribution that is um, a distribution like this has a much lower variance than a distribution that is like this, because this has a lot more points that are far away from its mean than this one is from its mean. And here, I mean, both the means fall along the same line, this center line. So that is the idea. If I'm messing something up, just let me know. I know most of you have been over this already. Hopefully that gives you like this hand wavy understanding of what mean is, what variance is, and what we're talking about here. So what we're saying is we want to consider these points and I want to weight these points higher when my prediction point is closer to them. Very simple to understand in that sense. Discounting imprecision. So Gaussian white noise. I'm not going to talk about the Gaussian distribution right now. I'm also not going to mention white noise right now. We'll get to that later. So that is, yeah, that is one of the other reasons we do that. Um, so he's talking about the assumption. So far we made this assumption of Gaussian IID white noise and homoskedasticity, which is why the OLS estimate is the maximum likelihood estimate, which is why it is a minimum variance estimator, and relates to this concept of best linear unbiased estimator. Read about it. I think we've already done that, but anyway. But in this case, the noise is not, magnitude of the noise is not constant, and the data are heteroskedastic. So that assumption is broken, which is why this estimate is no longer the most efficient way to go about it. And so we want to do something. So forget the rest of this, read this. So as the local noise variance increases, what we want to do is weight of the data point should decrease. So it should be inversely proportional. And the simplest way to set this is use the constant one, and then say this is equal to 1 by whatever, the noise variance. So that is what they do here. And we get the heteroskedastic maximum likelihood estimate and recovery efficiency. But that, like, we go into the details of this later on, so don't worry about that. He explains it in plain English. Trying to give equal attention to all parts of the input space is a waste of time. We should be more concerned about fitting well where the noise is small and expect to fit poorly where the noise is big. Simple enough. Another part where noise variance might be high, or heteroskedasticity comes into the picture. Not high, but like different. Um, Heteroskedasticity happens when the sample is a biased representation of the population. So if you give only university students a survey about how do you like university or what do you feel about university, as opposed to, uh, that's a bad question. That's a bad way to frame it. This goes back to random sampling. Um, when you have a particular pop distribution that you want to sample from, you want to pick data points randomly so that you cover, and I say pick in the sense like this is your distribution. By drawing these lines, I'm indicating that I'm sampling these values of X and Y. And by doing it randomly, I basically choose, in some sense, evenly from across the distribution. Um, And if the probability of obtaining, if this is a probability distribution, oh man, there's too many concepts I'm getting into here, so forgive me if you're confused by this. uh, how do I okay, so if you're testing people for COVID, you want to take a random sample of people because COVID could be anywhere with anyone. So you don't want to only test healthcare workers and say, oh, okay, this is in general holds for the population. You want to test restaurant owners, you want to test people on the streets, you want to test people in colleges, and so on and so forth. So if you only test one particular sample of the population, that is the bias you are introducing. So that's what this means. By doing selective sampling, the sample might be a biased representation of the population, and then this case typically occurs. So hopefully that was clear. If not, again, interrupt me, please. Um, Always happy to be corrected, always happy to be interrupted, and people have very frequently corrected me in the past, so I feel very happy when that happens. Okay, cool. Um, he also mentions covariate shift, but right now we don't have to go into that complicated a concept. Um, okay, cool. And then the final reason for actually doing weighted least square is, well, some other idea where the one of the key concepts we'll get into later are what are generalized linear models, and like in this, where is the weighting coming in? Yeah, I don't want to get into more details here. I'm trying to keep this low level enough. Again, Aryan and Deep, this is your first lecture and you're jumping into chapter 10, so feel free to ask questions if you're confused about any term, any equation, any sort of definition that I'm skipping over and not going into. Um, so this is the idea that we've been discussing. Suppose the noise variance is itself variable, and it follows some sort of distribution that we want to discover. Um, Gives an example where, okay, if this is the response by this particular case, the OLS estimate, standard errors. Okay, so this is the true regression curve, and you add some noise to it. So when I say the true curve, so yeah, I should get into this definition of true model and like fit. So particularly Aryan and Deep, the way we do analysis in statistics is you write some true model, you write some random noise added into that true model. So that's why if this is the true model, every point won't lie on this line, but it will be drawn from the x, the y value will be drawn from the x plus a particular noise term, which is why it varies. So that is the idea behind this true line, these points drawn from the true distribution. And then when we actually do fitting, we just see these points. We don't know what the true line is. And then we fit our estimator, and obtain an estimate of the true function. So that is the that is the statistics way of going about experimentation. Hopefully that's clear. So again, in machine learning, you just get data and you make some fit to it, assuming that there is a true function that this data comes from, or the true data generating process, different terminologies for it. And our goal is to get a fit that is close to that true data generating process. Um, yeah, I don't think I want to say anything more about that. So that is how fitting is. And he goes on to say that, however, we have assumed that the noise is homoskedastic, which it isn't. Did he give us the equation for this? No, he said figure it out yourself. So, okay, the concept of residuals. Okay, so far we have assumed that the um, so in a normal, well, I say normal, in the linear regression setup for OLS, we assume that the noise is homoskedastic. What does that mean? It has a fixed variance, constant variance. You typically see this term sigma square as the noise variance. So we assume sigma square is constant for all I. Um, But now what if this is not constant for all I? What if there is some structure? Then when you fit your curve, so when you say we assume y will be equal to some x beta plus noise epsilon, um, and we obtain a particular estimate for this beta, let's call it beta hat, then what you're saying is this is the best fit. If you do this using OLS, what you're saying is this is the best fit that we can obtain using this data. And what we're also saying is because we've assumed this noise variance is fixed, then the residual. So the residual is defined as in the, you can use the English meaning of residuals. Sorry, y minus x beta hat OLS. And we squared, we don't have to square it, this is the residual, and then we talk about the squared residuals. But anyway, the residual is what is remaining. Like once we fit our function, what is the remaining stuff that we can't explain? And by definition, that remaining stuff is the noise that we can't actually fit. And note that when you're talking about overfitting, what you're saying is you're also fitting the noise, which is wrong. Noise isn't supposed to be fit, it is supposed to be the part that you can't fit. By definition, it's noise. So what you're saying is this remaining term is called the residuals. And we talk about the squared residual. And what you're saying is because this is noise and we can't fit this, um, however, we know that this remaining term will have expected value 0 because that was the assumption we made. Expectation of epsilon is equal to 0. So you hear 0 mean noise, Gaussian noise. So that means that the noise is drawn from this Gaussian distribution where the mean is 0 and the variance is 1. I can't really show, but yeah. Um, that is what you mean by, I guess, white noise. Um, what else do I want to say about this? So what you're saying is if what is remaining is noise, and if noise was drawn from this distribution, then what is remaining should be drawn from this distribution. So it should have a constant variance and it should have a 0 mean. Um, and if it is not having constant variance, so if the squared residuals, variance is defined as square of this distance of each point from the mean, if you remember correctly. Um, and so if it does not follow that, then that means this assumption is wrong. Does do people follow this? Like this is proof by contradiction. I think that was 10th or 12th grade calculus. If you don't interrupt me right now, I'll pause.
No, I understood. Yeah.
Okay, cool. So he's saying that this is the assumption under which we operate with linear regression. So if you fit this OLS regression, and if your residuals do not follow this distribution, then that means that noise might not be homoskedastic. There is a subtle other point about the fact that your true function might not be linear in the first place, because by doing linear regression, you're making the assumption implicitly that your true model is also linear. It could be any sort of line, but it is a line. That's the idea. No? Yeah. So that could also be the case, but here we are assuming that true model is linear, and then if this noise variance is not constant, then we have an issue with homoskedasticity and heteroskedasticity. So that's what we focus on mathematically analyzing. And he's mentioned before also that you should always plot the residuals against x. So when you plot the residuals against x, you see that, oh, so for increasing x, the value of residual increases, which means there is some sort of problem that we have in hand here. The residuals have a structure, which should not be the case. So the way, okay, so now the way this goes back to like how we analyze a lot, we spoke about bootstrapping, but this goes back to this idea of what is the best thing you can do if someone gives you some data um, um, and asks you to fit some model to the data. So you can take the data, assume some sort of, make some sort of assumptions like this is a linear model. We use a linear model to fit this data. Assume the assumption you're making implicitly is that the true model belongs to a class of linear models. So when you're doing like the way like mechanistically, the way you do this is like, and this is an important coding example, just from the perspective of understanding how this goes about. So you define a true model for the data, y is equal to 3 minus 2 star x. Then you add some noise to this, where your noise, you want n noise terms, your mean is 0, and your variance is, and s apply is just a function you apply for to the variance, where you make the variance a function of x. So you are saying this is equal to 1 plus 0.5 x square. So this is heteroskedastic noise because the variance is not constant. Typically, you would add noise with 0, 1, mean 0, variance 1. That is your IID white noise. But no, here you're saying make the variance a function of x. So you define your true model to be heteroskedastic. And then without actually knowledge of that true model, you say, okay, now just fit my y to this data x and see what I can obtain with a linear model. And then what you're doing is return, you know these true parameters because you wrote the true model. So you say this, I know this is my true mean for the parameters. So the coefficient of x should be 2, the intercept term should be 3. So return how much my fit varies from this true model. And you repeat this 10,000 times to get these SE terms. SE just means standard error. So that's how these simulations work. You first define a true model. Without knowledge of the true model, fit your parameters, fit your parameter estimates, obtain your parameter estimates by fitting your model to the data. Very technical terms, but important. And then once you have that fitted parameters, compare them to the true values and see how far you are. And then once you repeat that, this you inherently just average out across these random iterations, and you get the standard errors of typically how far am I going. And so the standard error relates to the variance of your estimates and the bias in your estimates. Um, yeah, I'm not going. Bias variance trade-off is covered extensively in the first chapter, and the second chapter, I think. So weighted least squares is a solution to heteroskedasticity. So suppose we visit an oracle, and oracle means you transfer information from here to your fit. So in essence, oracle is like your, someone tells you the true values, or someone tells you this true function for the noise is 1 plus half x square. Then what we can do is we can use this function for the noise variance. We know that this is the true function. We can use this to improve our fit by doing weighted least squares. And then they get into the math of how weighted least squares works. Qualitatively, the reason weighted least squares with inverse variance weight works is the following. OLS tries equally hard to match observations at each data point. Remember, OLS was unweighted least squares, which was like treat every point equal, fit your model to every point using those uh, the least squares laws. On the other hand, weighted least squares, oops, naturally enough, tries harder to match observations where the weights are big and less hard to match them where the weights are small. Again, we've been over this, but it is important to mention this again. So the noise terms have large magnitudes where the variance is large. So we should want to have small weights where the variance is large. Um, so again, it gets to the point of why this is inversely proportional, basically. But now he asks, but why not like 1 by noise, 1 by standard deviation of noise? So why this sigma square term? Why not 1 by sigma xi for each noise term? Which is also fair. Like this is still inversely proportional. So why are we using this squared term? And of course, like for different problems, arbitrary choices of weights could work like differently. So you have to check it for your problem at hand. Um, and okay. So they go down into an analysis of why they choose this in a general case. And to avoid like confusing you, you can skip over this section. I'll just spend 5 minutes explaining it to everyone else. Okay, so the beta hat estimate. So remember that I, I guess he's discussed this before. But if you recall the closed form solution to linear regression, yeah, the closed form solution to linear regression was x transpose x inverse x transpose y. So given a set of data with terms xy, where x is your covariates and y is your response. This is the closed form solution for your OLS estimate. And now once you add weights, this turns out to be a new closed form solution, including those weight terms. So using that, it goes down to say this. So this becomes your new weighted WLS estimate. Um, and if you write this x transpose x, x transpose w x inverse x transpose w as HW, then you obtain your estimate. I mean, I've written some notes about this, so if you're confused about why this is the case, then this is what your estimate turns out to be. So your estimate turns out to be the true beta plus some x transpose and plus some terms times the noise. But if you take the expectation of this entire thing, then because expected value of noise is 0, remember that noise is still uncorrelated. That's it. Uh, Generally uncorrelated. I need to think about this. But okay, if you're saying it. uh, So expected value of noise is 0. So the WLS estimator is unbiased. Now unbiased, I thought I wrote about this. Unbiased is when, so you get your data, you make an estimate, and what you're saying is, if I repeat this enough times, and then the expected value of my estimate will converge to the true value. Or you're saying that over, if I run this enough times, then this and I average out over the noise, then this estimate will be 3 and this estimate will be 2. So my fit coefficients will, the expected value will be 3 and minus 2. Mm, yeah, it will give you a better introduction to expectation and variance. So because of that, this WLS estimator is unbiased. And in fact, for the jth coefficient, it is unbiased. I guess you're saying the same thing then. So each coefficient estimate is unbiased. Is that the point here? I thought that was straightforward. Oh, okay. Um, so of course this is unbiased, but the natural next question is like, what is its variance? Because if it is unbiased, but it still has a very large variance, then our estimates are still likely to be off if the sample sizes are small and if we don't repeat the process millions of times. So we want it to have a small variance, and we obtain an equation for the variance using which, according to the Gauss-Markov theorem, we can find the optimal weights that has the unique solution, Wi is equal to 1 by sigma square xi. And he does give us the math for the Gauss-Markov theorem, but I don't want to get into it in the interest of like confusing the others and also time. I've given you some sort of ideas of how to go about this if you don't have any idea of what normal distribution is, what log likelihoods are. But yeah, sadly, I'll skip over the math this time, but we can come back to this once we're done with the review, because this Gauss-Markov theorem is super important. Um, it, Basically like this theory of what is an estimator, what is an estimate, what is minimum variance estimator, what is best linear unbiased estimate. Like that comes up a lot when you're trying to figure out efficiency in estimates. Like you can have an estimator that does anything. Like I can have a constant estimator that no matter what data it gives me the same values, but that is a bad estimator. You want to find an estimator that works, that scales, that does not have high variance, because you don't want it to like give you different answers each time you repeat the process, where the data does not vary that much. So that is this idea of minimize the variance in the estimate. So if I have similar data, I want similar estimates, and high variance would mean might not get similar estimates. That sort of. Um, yeah. So that's all I want to say about that, and I will probably skip over. Like there are a lot of nice things about this, and I wanted to get into it, but never mind. So back to the top, like all of this was possible because the oracle told us what the variance function for the noise was, right? Someone told us that, okay, use this for your noise variance and you will magically end up with the right model, right fit. But what if we don't know what like this, and this is called like a, do I want to get into parametric, non-parametric models, right? He does mention non-parametrics. A parametric model, um, again in a very hand wavy sense, is one where you have some parameters, so some coefficients for some polynomial that you can imagine it to be. So whereas a non-parametric model, on the other hand, you can imagine it as like a class of different. Um, there's a lot of pack. Well, maybe I'm just.
Maybe they could understand it by maybe you can explain non-parametric as k-means. Like I think most of them would understand k-means.
That's a great point. Okay, so in like if you're familiar with k-means clustering or k nearest neighbors k-means clustering, the idea of this k varying, um, so you can learn the parameters of k-means clustering. Like this k is not in k-means k is fixed though. But no, you want to go ahead and explain it? I'm probably not good at this.
Yeah, sure. So I mean, I think I would be able to explain it using example. So linear regression would be considered a parametric model, whereas something like k-means is because we have a parameter, right? We don't like we don't have, I mean again shit. Sorry. It's not something that you fit according to the data, I would say, right? Maybe.
Mm-hmm.
I think that's
Uh,
the.
can I fill in just really quick?
Yeah,
Like,
please.
I think you guys are already on it. It's just parametric models, like you guys saying, they have a finite number of parameters, right? So that like in regression, you have the slope and the bias term, and a non-parametric model, you assume an infinite number of parameters. And the idea is that you assume there are an infinite number of parameters, and then the learned model will reveal what sort of number of parameters that you actually end up learning. So the best example that you guys were considering earlier was k-means. The reason k-means is sort of non-parametric is not really to do with like, so drawing sort of relationship is a bit difficult there. So if you consider a k any mixture model, right? So let's say you have a finite Gaussian mixture model. There you have to define what is the number of clusters that you are seeking. So you have to fix the model to with a finite number of Gaussians that you want to fit. Whereas in non-parametric versions, like I'm assuming you guys probably don't know, like Dirichlet process, like if you put a Dirichlet process prior. So, but k-means essentially says that, okay, let's not put a number of um, um, uh, sort of, you don't predefine anything, right? Let it evolve, and then at the end you do get a finite number, right? But you just don't define it a priori. So non-parametric is a big confusion. Never think it doesn't mean there's no parameter. It just means there are infinite parameters. So like a Gaussian process is also non-parametric. And the simple example is take Gaussian mixture model and don't assume or predefine the number of clusters. Set that to infinity, run the inference method, and find out what it is.
So that is an excellent explanation. Thank you. To give you this, like the first time I came across this, my confusion was, but then why not use non-parametrics everywhere? Like, why do we want to? So we mentioned that when you're doing linear regression, the underlying assumption is the true model is linear, because otherwise it can't capture. Yikes. Okay. I lost my screen. It'll come back hopefully. Oh man. So I can just talk you through it in the meanwhile. So the uh, the natural question that I got in my head when I was like non-parametrics was like, why don't we use it everywhere? But the only caveat we have is because you assume these infinite parameters and then you reduce yourself to the space of finite parameters. That whole learning process is requires a lot of data and is computationally expensive. That is the only reason, like, you can't just throw it at every problem and say, okay, learn the parametric models for me using this infinite set of parameters, reduce it to the space. So and we did like an extended discussion on these aspects before, so there are chapters that will cover that for you, so don't worry about that. But hopefully that gives you a at least an idea of what they're talking about in this chapter. We were on, oh no, oh no, 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 no. Okay, I lost all of my notes. Life is extremely sad. Whew. Okay, so it's on my iPad. So I need to quit this. Restart it. Hopefully it will ask me which version I want to keep. Oh, come on, man. This is so annoying. Um, well, I guess I can at least walk you through the, man, even forgot where I was. Non-parametrics, okay, okay. Some notes are back. Huh. Okay, cool. Um, well, Gauss-Markov theorem proof, we skipped over this. We came to this idea of, did we? Thanks. So parametric, non-parametric models. I forgot where I was. Yeah, okay, so we were here. All of this was possible because the oracle told us what the variance function was. What do we do when it is not available? Sometimes we can work things out for ourselves. Sometimes we know things. So we know about the process that is creating the data generating process. So we can figure out how the noise variance might vary. We know that the noise must depend on the input variables. For example, in polls or surveys, the variance of the proportions we find should be inversely proportional to the sample size. So we can make, so smaller sample. Again, you'll get into this before, but there is a difference that large samples and small sample sizes have some differences in variance, which will be explained by some mathematical formulas. But anyway, what the larger point is, like, sometimes we know how it's going to change. um, and that brings us to like the conditional variance, and like what the conditional variance is essentially saying is that if the noise varies as if the variance of the noise varies as a function of x, like That is the definition of heteroskedasticity. I thought I made some plots here. Man. Yeah. Anyway, um, so to start from the top, there are two generic ways to estimate conditional variances. And again, why conditional variances matter is because this noise variance is now no longer this sigma squared. It is sigma I squared, where sigma I, um, each of these is a function of the respective xi. So that's what equal to f of xi. Hopefully this makes a little bit of sense. Um, and so what we want to do is we want to estimate this conditional variance function. So we want to figure out what this function for the noise is like. And the way we do this is start by doing your standard OLS estimate and getting your fit, getting your estimate for the mean of a conditional mean. Again, this you will see why um, this is covered in chapter 1, so I'm not going to, again, extensively covered in chapter 1, so I'm not going to go into why this conditional mean is the OLS estimate. But if you have some data, if you use OLS, then this is the best estimate you're going to obtain. Um, um, that's what you get. So what it's saying is first get that, then construct the squared residuals. So we already spoke about this, what the residual was, but like the remaining value that you can't fit. So yi minus mu hat of x the whole squared. Then using your favorite non-parametric method, then you estimate the conditional mean of the ui. So you fit the model to this squared residual and see what sort of distribution that gives you. And use that distribution to predict the variances for each point. I had notes here, damn it. Okay, and use that fit of those squared residuals to go back to your original data and say, okay, look, now this is possibly how the noise variance is varying. So that's, and if you keep doing that, and then you can use weighted least squares using that fitted noise variance to repeat this process up and down. And that's what he's saying, that okay, so use a regular model, find the residuals. If the residuals don't fit this homoskedasticity assumption, then you fit those residuals using a non-parametric method. You learn this function that will tell you more about how this noise is structured. Go back, use this function to predict that, okay, this is potentially how the noise variance could be. Now that will change your original function. So you will have to refit this. Then you can do weighted least squares. Learn new parameters, go back, fit the residuals, and eventually this procedure will result in some sort of convergence. And he also defines this convergence mechanistically later, which is really nice. But again, I'll get to that later. What he says is alternatively, and this book is nice in the sense that he focuses on practical tips just as well as the theory. Unfortunately, it's all in R, so you will have to rely on me to explain some bits of code. But I will do that from time to time. And if anyone wants to learn R, I'm more than happy to do a tutorial on that, although I'm not an expert. I just learned it for one semester last semester. Anyway, so hopefully this idea is clear. Fit model, learn variance structure, fit model, learn variance structure, fit model, learn variance structure, hopefully converges. Questions?
Could you share the screen? I can't see where you're
Oh,
reading from.
great point. Sorry. Thank you. Thank you very much. Um, yeah, so this is what I was talking about. So estimate the conditional mean, construct the squared residuals, fit the squared residuals, use the fitted values to predict the variance of the original noise and repeat. And the second part, the more practical idea is he's like use the log just for more stability. And when people say, so this entire idea of why use log likelihoods and why use all of this is because these numbers vary a lot. So when you take the log, you restrict it to some sort of reasonable intervals, or at least reduce them from varying as much as they would if you hadn't taken that log. Um, Plus, it's not that expensive to consider to construct a log of a function, whereas it is very expensive to work with super high decimal spaces. And you can just do that by working with like checking how float, double, long performance works in PyTorch or something. But anyway, so the same method, different sort of approach to using the log. Um, but that is a high level idea, this iterative process of, and then it converges. So he explains the same thing in nice English. Again, this is really nice about the structure of the book. If you read every line, in this case, you will actually understand what the theory means. And in a lot of books, that's not the case. But yeah, that is the idea. So please read the English explanations after the math gets over. Um, and yeah, he says this usually will converge. So you have to think about what does convergence mean. And I thought I highlighted that, but evidently not. The convergence basically means like your estimates will change a little bit, and at some point that change will become very tiny. So that is your definition of convergence in this case. And by your estimate, recall that your original parameter estimates was beta naught was 3, beta 1 was -2. So like 3 plus 3 minus 2x plus noise. That was what you were using, 2x square, right? Minus. No, I don't remember anymore. 3 minus 2x square. Well, you can always go back to the code and look up what he was using. But okay, in the interest of time, I'm going to skip that. Um, he takes a nice real example. Um, but before that, like again, like the way we get our standard errors is by repeating this process multiple times, like this entire process of simulating data, getting some estimate, re-estimating, changing this iterative process. Again, sampling data, estimating, sampling data, estimating, iterative, whatever. So just the general approach to getting standard errors and confidence intervals that you will look at extensively in the bootstrap chapter. um yeah, I'm not going to get into what the bootstrap is right now. He takes a practical example that I would highly recommend you read through. It is nothing special, like it is the same thing, your data variance, heteroskedasticity, then fitting this, and he gives you some ideas. The general, like the important takeaway from this is, if that whole diagram I drew about if it was a homoskedastic model and if homoskedasticity doesn't hold, that is explained in this picture, where he says like if you have a homoskedastic model, most of the time this is what your noise variance will look like. It will be constant, and sometimes it might vary, like these light gray lines. This one is the dark gray line, so I will draw it separately. But other than this red line that I'm tracing very poorly, other than this line, like these are all simulations from a homoskedastic model. So again, this proof by contradiction that I mentioned earlier, this is the mathematical version, like the simulation version of it. Like you simulate from a particular model, and if your real data does not match that, the variance of the actual data that you get is not belonging to this class. And again, that goes into hypothesis testing, which we've also discussed extensively before, so I will skip that. But he's saying if it varies a lot from this general case, then that means this general case is false. So that is why this noise is not homoskedastic. Um, anyway, read through that example. This, oh man, I lost my notes on this also. So super annoying. Um, I made really nice notes on this section. Okay. What is he saying here? Resampling the residuals, bad distribution, and the heteroscedastic. This is not the case. Nonetheless, you can still resample to get bootstrap conflicts intervals provided we define and scale them properly. Okay, so he is saying the same method that we were talking about before. Um, Typically, we assume that the distribution of fluctuations around the regression curve, and this is again different ways of getting at the variance, um, or the conditional variance. This is homoskedasticity. If the distribution is the same for all values of the input x, under heteroskedasticity, this fluctuation is not constant. So that is, I guess, the plain English way of saying conditional variance um, obeys a distribution that is not constant, I guess. And he's saying if this is not under heteroskedasticity, this homoskedastic assumption fails. That is fair. Still, we can resample residuals to get this bootstrap confidence interval, standard errors, and so forth, provided we define and scale them properly. If we have a conditional variance function as well as the estimated regression functions, we can combine them to resample heteroskedastic residuals. So what he's saying is, before what we did in this, I guess I covered that at once as opposed to waiting for this. Where was my two methods? Ugh, okay. Never mind that. What he's saying is first construct the standardized residuals by dividing the actual residuals by a conditional standard deviation. So estimate this standard deviation, divide the actual residuals by the standard deviations to get this idea of standardized residuals. So you're essentially making them all the same magnitude by assuming that you know this true function. Um, yeah. And then using the distribution that you obtain thereafter, you can resample this standardized residuals to obtain a new set of standardized residue. Yeah, a new set of samples for the residuals. This is like, I don't know an easy way to explain why we're doing this. Why are we bootstrapping this to get the standard errors? I guess you can think of it as another example of this iterative process that you follow. You make some assumptions, you fit some model to your data under those assumptions, but now you want to check if these assumptions are true. So you use this fit to resample this data, and you fit the new data, um, treating it like it was real data. And this repeating this process multiple times gets you back to this idea of bootstrapping and gives you confidence intervals. But like, I've used a lot of jargon here, so if you haven't studied all this and you don't follow, that's fine. We had an entire chapter on bootstrapping and confidence intervals, so we will go back to that. But hopefully the rest of you at least follow that much. It's similar to the process we described before, except now you're standardizing the residuals, assuming that you know this function, or use an estimate of the conditional standard deviation. So we used the conditional variance before, we now divide by the standard deviation and multiply by the standard deviation later. And yeah, that gets us to local linear regression. And okay, I'm going to stop here because I really made some notes for this that I need, and I don't seem to have them for some reason. Ah, yeah, I'll try to get those back. But the high level idea for local linear regression is, you can think of it as, oh man, I keep harping on this, but okay. Local linear regression is exactly like you consider a closer set of neighbors, do linear regression there, fit a line. Consider a closer set of neighbors, do linear regression, fit a line, and so on and so forth. If you have points like this, then you fit a line here. You have more points here, you fit a line here. You have more points here, you fit a line here. As opposed to just taking all of them at once and trying to fit a line like that or like that. I don't know how it will be, but that is the idea of local linear regression. He goes into a lot of analysis of the math behind it. most importantly, how it is subtly different from kernel regression, because it starts sounding like kernel regression a lot. And this is the important question that he, uh, this is the important question that he explains why would we use local linear regression if we already have kernel regression, and pros and cons of it. One of the ideas was when we speak of the Taylor expansion. Man. Okay, I'll save the section for next time. We can stop here and we can go back into the important discussion we had to have here with Akash. But I will pause for questions before that in case anyone has anything before local linear regression. What we discussed. To summarize the chapter, like what is the difference between homoskedastic and heteroskedastic models? What does the noise variance varying really imply? What are the methods to sort of firstly figure out whether that assumption holds homoskedasticity? What if it doesn't hold? This iterative method of using weighted least squares. Um, the the fact that the weighted least squares also gives us an unbiased estimate and has the minimum variance. Then we looked at, okay, so now if I have this, how do I get confidence intervals? How do I tell? And the importance of confidence intervals is it gives you a sense of how right you are, because just getting one set of parameter estimates tells you close to nothing about the uncertainty that you have in your estimates, because you don't know what happens if I do it again. So you do it again and you do it again and you do it again and you keep doing it until you finally can say, okay, so I've done this enough times to get the average sense of what happens, what are these estimates roughly varying between, and how right my assumptions are about the data. And then he says, if you think you are right, then use your assumptions to create a new model, sample from that model, refit, and see how much your estimates change. Like keep doing that again and again. That is the idea of bootstrapping. But yeah, questions? Okay. If there are no questions, we can jump into using Akash's time better, um, and talk about like, oh, first off, could you introduce yourself to them, like just
Absolutely, yeah. I should also first say that at this point, thanks to Swapnil, I think you all know more about